In physics and in chemistry, but really more in physics, we're going to be doing a lot of measurements that involve a lot of numbers and calculations. Now, in those measurements and calculations, we have two large sources of error. We got the sources of error that occur from the lab instruments themselves, and we also really have to account for the human error, the ability to perceive something as soon as you observe it and then record that perception. It always takes a little bit away from the data. And because of these large sources of error, we have always degrees of uncertainty when it comes to our numbers and figures in the calculations. And it's because of these degrees of uncertainty that we have to be aware of something that we call significant figures, or in some classes, significant digits. In scientific data collection, it really all comes down to accuracy versus precision. Accuracy describes how close your data set is, or your data collection, or the numbers and calculations that you get, how close they are to the correct result. Or in the science world, we call that the theoretical results. In chemistry specifically, the theoretical yield. In other cases, we measure how precise your data is, whether it is close to a theoretical result or an accurate result or not. You may have experiments where the same numbers are repeated, and so we could still argue in some cases that those results are indeed reliable, but we say that they're precise and not accurate. And so when we need to describe precision, we're talking about how often you get the same result. When it comes to taking lab measurements, the last digit often is a best guess, especially when you're dealing with a number that has several decimal spots. And so what we say is that all recorded measurements and data is considered significant, but the last digit, specifically when you're dealing with larger numbers and values or numbers with a lot of decimal spaces, are going to be deemed uncertain. And so to help us identify all the significant figures and digits in a data set or in measurements that we take, we've come up with a set of significant digit or figure rules that we tend to apply between most of the math and sciences. The first rule when assigning significant digits is that all non-zero digits are considered significant. So for example, if I have a number like 512, 5, 1, and 2 are all non-zero digits, and so each of those digits are significant. So if the question were to ask how many significant digits are there in 512, you would say 3, 5, 1, and 2. The second rule is that zeros between non-zero digits are considered significant. So if I have a number like 2005, I have 2 and 5, which are non-zero digits, and then between the 2 and the 5 are 2 zeros. Well, in this case, specifically, the 2 zeros are also considered significant digits. So the total number of significant digits in a number like 2005 is 4. 2, 0, 0, the numbers that are occurring between the 2 and the 5, and of course 5 itself, that is 4 significant digits. The third rule for assigning significant figures and digits is that in a non-decimal number, the zeros to the right of a digit, right, of a non-zero digit, I should say, are considered insignificant. So if I have a number like 2400 or 2400, the 2 and 4, of course, them being non-zero digits, are going to be considered significant, but then the 2 zeros to the right of the 2 and the 4 are considered insignificant. And so the total number of significant digits in 2400 is going to be 2. And this is specifically the case with chemistry and physics. The fourth rule when assigning significant figures is that any zeros to the left of a non-zero digit are going to be considered insignificant, whether they are decimals or non-decimal numbers. An example of this would be, let's say I have the number 0.0092. Well, 9 would be the first non-zero digit despite it being before the decimal point. Well, the 3 zeros that occur before the 9 are considered insignificant. And so the number of significant digits in 0.0092 is 2. Now, the fifth rule when assigning significant digits or figures is that when we have a decimal number, any zero to the right of the last digit in the number is going to be significant. That includes any zeros after the digit in a decimal or after the decimal point. So if I take, and I'll give you two examples here. Let's say we have the number 250.0. Well, those two zeros come after the 5, which is the last non-zero digit. Now, because it is a decimal spot, those two zeros are significant. If it was 250 without a decimal, that zero would not be significant. But once the decimal is placed in there, any zero that comes after the last digit is going to be considered significant. So in a number like 250.0, the 2, 5, 0, decimal, 0 are all significant figures. That means that this number has 4 significant digits. So let's take a look at these 5 examples of data sets and determine how many significant digits are in each number sets or data set. So let's say the first one, 1600. Well, this is a non-decimal number. And if it's a non-decimal number, then any zeros like these two over here that are to the right of the number are insignificant. So this is not significant. But then applying the first rule, where any non-zero digit is significant, that leaves us with the 1 and the 2 that are significant. So we have 2 significant digits over here, or sig digs. If I look at the next one, 2026. Well, a couple of things. First of all the non-zero digits are significant, so we automatically have 3. And then this 0, it really is dependent on what else is going on. Now, because this 0 is in between two non-zeros, the 2 and the 2 over here, then it is also significant. So this one has 4 significant digits. 1, 2, 3, 4. Let's look at the next one. 0.47. Now, this over here is a decimal number. And so what that is going to do is affect any possible zeros that come after the digit. Now, in this case, the non-zero digits, which are always significant, whether they're decimal or not, are the 4 and the 7. And so I know that we already have 2 significant digits. Now, that 0 is really what's in question. Since the 0 is to the left of the non-zero digits instead of to the right, then it is insignificant. And so this would only have 2 significant digits. Now the final 2 number sets here, 0.0039. If we look at this one, again, any non-zero is going to be significant. So we have automatically 1, 2. Now, once again, we're going to look at these 3 zeros that follow it and ask ourselves, are they to the right, meaning this way, or to the left of the last digit in this number, namely the 9? In this case, because they're to the left, they are also not significant. So this one would only have 2 significant digits. And then finally, with the 200.0 number set here, this is a decimal number. And so while the non-zero is automatically significant, because it is a decimal, we have to carefully look and see where the zeros are placed with regards to the final non-zero digit, in this case, the 2. Well, since these zeros are to the right, and it is a decimal number, then they are considered significant. So remember, any zero that is to the right of the final digit in a decimal number are going to be considered significant. And so this has 1, 2, 3, and 4 significant digits.